Key features of linear functions. So the last lesson involved domain and range. Now we're going to be introducing some more features within linear functions. And a couple of them are your y-intercept and your x-intercept. So y-intercept is where the function crosses the y-axis. We've been dealing with that. Now this sort of concept is going to be important. Now remember, where it crosses the y-axis is also where x equals 0, right? So wherever it crosses the y-axis, it's where x equals 0. And then for the x-intercept, it's where it crosses the x-axis, or vice versa, where y equals 0. So that's going to be kind of an important concept to recognize when we do this. So number one says, write both the x and y-intercepts for the following graphed functions. So the y-intercept on this function here, so I'm just going to label y-intercept, is right here. It's at 5. And I'm going to write it as a coordinate. So that coordinate would be at 0, 5, which kind of falls into the idea I've talked about earlier up here, is it's when x equals 0, right? We got a 0 in for x there. So that makes sense. And then let's get the x-intercept. That's where it crosses the x-axis, which would be down here, which I'm going to write this as a coordinate, which would be negative 8, 0, which again kind of falls in that concept we talked about earlier, is the x value is 0, or sorry, the y value is 0 at the x-intercept. So those are the y-intercept and the x-intercept. So I'll let you write the y-intercept and the x-intercept for B. Now, let me show you how that kind of looks in a table. Okay, so in a table, you can't really see it, right? You can't really see it. Now, surely you could graph it on some coordinate paper. But let's just use that concept of what I was talking about earlier. If you want to find the y-intercept, it's when the x value is 0, right? Like on this example up here, the y-intercept was, up here at 0, 5. So if you want the y-intercept, it's when the x value is 0. So if we look at this table, the y-intercept is here because x is 0 at that spot. So the y-intercept is at 0, negative 12. And the x-intercept is when the y is 0. And the y is 0 right here. So the x-intercept is at 3, 0. So that's how you can identify your x and your y intercepts from a table. So keep that in mind. So wherever the y-intercept is whenever x is 0, and the x-intercept is whenever y is 0. So let's continue that sort of idea when we have an equation. So if we're trying to find the x and y-intercept with an equation, we can use that same logic. So 3 says to find both the x and y-intercepts of the following functions. So letter A, you can probably already identify the y-intercept because it's in y equals mx plus b, right? It's 10. The y-intercept is 10. But let's just humor me here. We're gonna do the math for it. So as you can see up here, what it says is to find the y-intercept, substitute 0 in for x. To find the x-intercept, you substitute 0 in for y. So let me do the y-intercept first. And again, we know it's 10. But if I were to follow those kind of instructions, I would have I'm going to label y-intercept. I would do y equals negative 2, substitute 0 in for x. Negative 2 times 0 is 0. 0 plus 10 is 10. So the y-intercept is at 0, 10. And then the x-intercept, we substitute 0 in for y. So I'm going to have 0 equals negative 2x plus 10, and then solve that equation. Subtract 10 from both sides, divide by negative 2, x is 5, so the intercept would be at 5, 0. Okay. So let me show you some more. I'm going to do C. I'll let you do B. Remember, f of x, this just pretend that's a y. You can change it to a y if you want. It's just function notation, but it still represents the dependent variable, that y-axis. So you can do that if you want. Okay, so the y-intercept. I'm going to substitute 0 in for x. So 2 times 0 is 0. So this is just going to be 3y equals 18. Divide by 3, y equals 6. So 0, comma 6 will be my y-intercept. For my x-intercept, substitute 0 in for y. 3 times 0 is 0, so I just have 2x equals 18. Divide by 2, x equals 9. So 9, comma 0 would be the x-intercept. E, let's do the same thing. Let's get the y-intercept first, I guess. So y-intercept, I'm going to substitute 0 in for x. 0 plus 1 is 1, so this is just 2 times 1. 2 times 1 is 2. Add 4 to both sides, that would be 6. So 0, comma 6 is the y-intercept. To get the x-intercept, you substitute 0 in for, whoops. To get the x-intercept, you sub 0 in for y. So 0 minus 4, I'm going to have negative 4 here. Maybe I'll distribute that 2, so I'll have a 2x plus 2. I'm solving for x here. I'm going to subtract 2 from both sides. I'll have negative 6 equals 2x. Divide by 2. Negative 3 equals x. So negative 3, comma 0. So just solving. Let me just do one more. Let me do g of x. Now, again, that g of x is our independent variable. It's just like our y. So I'm just going to pretend it's a y. So for a y-intercept, plug 0 in for x. I'll have a negative 1/2 0 plus 7. So negative 1/2 times 0 is just 0. So this is just 7. So 0, comma 7. And again, this was in slope-intercept form, right? So we could have identified it as 7 right from the get-go. Now to get the x-intercept, substitute 0 in for y. I'm going to solve for x, so I'm going to subtract 7 from both sides. So 0 minus 7 is negative 7. And then divide by negative 1/2 to solve for x. You could multiply by negative 2 as well, but I'm just going to divide by, so negative 7 divided by negative 1/2 is positive 14. This is 14, comma 0. And there you go. So that's how you can do it with an equation, okay? So that idea of y-intercept, at the y-intercept, the x value is 0. And at the x-intercept, the y value is 0. That idea is critical when you're trying to identify the x and y-intercepts, rather it be a graph, a table, or an equation. So keep that in mind. Now, the kind of last key feature we're going to deal with. So we dealt with domain range, x, y intercepts. The next thing that we're going to deal with is the n behaviors. Okay, n behaviors, and n behaviors is it's kind of self-explanatory in the word. It's the behavior of the graph at its ends. Okay. So, when we have these continuous linear functions that kind of go on forever, if the slope is positive, like we have here where this line is slanting up, as x increases, y increases. As we go to large values of x, as we go this way, the y is also going up. It's also increasing. So as x goes to positive infinity, y also goes to positive infinity. And a similar concept kind of happens as we look in the negative direction. See, as x decreases as we go this way, the y also decreases. It's going down. So as x goes to negative infinity way out here, the graph is also in the y direction going down to negative infinity. So like when we're thinking about the infinities, try to be a little bit more clear. Like up in this direction, we would say this is the x direction, positive infinity, and then the y direction is also going up to positive infinity. And then if we'd say down here in the x direction, negative infinity, it's going down to negative infinity down here. Now, if it's the slope is negative, it's a little bit different. As you can see, as x increases, as we go this way, it's not going up. It's not going up this direction, right? It's actually going down. As x increases, as we go this way, this graph is decreasing. Y decreases. And vice versa, as x decreases, as we go this way, y is actually now increasing. So in terms of this sort of infinity concept, when that slope is negative, as x goes to positive infinity, this graph is going down to negative infinity in the y direction. And as x goes to negative infinity, this graph is going to positive infinity in the y direction. So let's apply it. Those were just some examples. Okay. Number 4 says graph the function to determine their key features. So this equation is written in point slope form. So first, let me identify the point and the slope. So the point is going to be at -6, 1. And then the slope is -1/2. So let me plot the point first. -6, 1 would be here. And then the slope's -1/2, so down 1 to the right 2 from that point. Okay. All right. Okay, that's pretty good. So let's determine the key features. So the domain, there's no restrictions. It's going to go all the way to the left forever, all the way to the right forever, all real numbers. Even the range, arrows on both directions. It's going to go up forever. It's going to go down forever. The range is also all real numbers. The x-intercept, remember, it's where it crosses the x-axis, and it looks like it crosses the x-axis at -4, 0. The y-intercept is where it crosses the y-axis, and it looks like it crosses at 0, -2. The rate of change is just a fancy word for slope, and we use the slope to graph it, so that's going to be -1/2. Now our end behavior. So it says as x goes to infinity, where does y go? It's got a blank there. So as x goes to infinity, out this way, out to infinity, it looks like the y is going down to -infinity. It's going down. As x increases, y is decreasing. Now, how about the other direction? As x goes to -infinity, as we go this way, it looks like the y is going up. So y is going to positive infinity. It's going up to positive infinity. So hopefully that end behaviors make sense. Yeah. Erase some of that. Okay. So I'm going to let you do the table. Remember, you're just going to plot the points. Now, it's going to be continuous. It's going to go on forever. So slap some arrows on the end of it after you plot the points, okay? But yeah, I'll let you do the table. I'm going to do 6. It says Abrielle started tutoring to save money so she could go on a summer vacation with her friends. She already had $100 saved. Then she charged an hourly rate for her tutoring. Once she had enough money saved, she stopped tutoring. Okay, that's an important thing. She stopped tutoring. So she stopped tutoring here. Okay. Her amount saved is recorded in the graph below. So it says, how much money did Abrielle charge per hour for her tutoring? That's referring to the slope. So if I kind of pick a couple points here, maybe here and here, some nice points, it looks like this increase here from 200 to 300, this is $100 for, how long is that? From 4 to 8 hours for 4 hours. So $100 for 4 hours, if you divide those, 100 divided by 4, that means she was charging $25 per hour. B says, write a function in slope-intercept form that models Abrielle's earnings after X number of hours. So I'm going to use y equals mx plus b because it wants slope-intercept form. So y equals, the slope's 25. So I'm going to say 25x. And then our y-intercept is our b, and that's at 100. So 25x plus 100, right? That's our y-intercept. C says, what's an appropriate domain for the function? Let me clear up some of this here. Let me erase that. So remember, domain is our x. You can't go negative hours tutoring. It starts at 0. And then she stopped after 16 hours. So our domain would be where x needs to be greater than or equal to 0 and less than or equal to 16. Now you could put on a stipulation where it could say like only integers, because you generally wouldn't tutor for fractional hours. I guess you could. So I'll just leave it at that. Now, how about the range? Now the range is asking about the y. So for this particular function, she started with $100, so she never had anything less than 100. And then she stopped at $500. So the range be greater than or equal to 100 and less than or equal to 500. That would be the range. So that's the domain. That would be the range. Okay. All right.